Well, hello, and welcome to Doc Onco's Physics. Keith Onco here. Today what we're going to be looking at is kinematics in one dimension again, except this is part 2. In part 1, I introduced displacement, velocity, acceleration, speed, position, and those are some of the real basics when we discuss kinematics, but they're critical to understand those things before we can move on and do some slightly more complicated things, again, simply in just one dimension. Now that one dimension can either be in the x direction or it can be in the y direction, but we'll stick to those two directions or dimensions. If we look over on the left-hand side, turn my pen on here. If we look over on the left-hand side here, what we've got are kinematics equations, and these equations are really just combinations of the equations that we started with in the last session, which were the voltage, the velocity equals displacement divided by time, right? Average velocity is equal to v final plus v initial divided by 2, right? And displacement, d, is equal to x final minus x initial. And of course, acceleration equals v final minus v initial divided by, not divided by a, divided by t. Sorry about that. Okay, so those are the basic equations that we started with in the last session. Well, what we're going to do is we're going to be combining some of these and rearranging some of these to create the equations we have on the left-hand side. And the equations we have on the left-hand side are going to be our tools that we're going to use to solve what we call kinematics or motion equations, or motion problems. Okay, so these are our basic equations, right? They're very simple. We want to expand those a little bit, combine them to form the equations over on the left-hand side. I'm not going to go through the derivations, but we're going to use them in a number of examples so that we can show you just how to solve a problem in kinematics. Let's look at the equations to start with. The top equation in this section here, and again, there's two sections here, right? One is constant velocity, where we have an acceleration equal to 0. And up here we have a constant acceleration, okay? And these equations apply to anything where we have a constant acceleration. Now, constant acceleration can also be 0. So these equations down here are really just special cases of the equations up on the top. For example, this equation right here, right? The change in position is equal to the average velocity times time. Well, if we look at an equation here, right? All right, we're looking for change in position, all right, is equal to the initial position plus the initial velocity times time plus a half at squared. Well, if we have a constant velocity down here, it means our acceleration is 0. That would cause that part to go to 0, all right? And if we start at the origin, that would be 0. And so our equation just becomes x equals v0 times t, v0 being the initial velocity, and that's what we have down, basically what we have down here. Okay, so these are special cases of the equations that we have up at the top. Right? But the equations at the top, those are going to be our toolbox equations. Right? You know, we can talk about an object moving at a constant velocity, say a bicyclist is moving along at some velocity. I'm a horrible artist, so you'll just have to bear with me here. And the velocity is equal to 13 meters per second, and the person travels for a time equal to 20 seconds, and we would like to know what the displacement is for that bicyclist. Well, if we assume that x initial was at the origin, 0, all right, we're looking to see where x final is. All right, we'd like to know what that displacement is. And what equation would we pick? Well, we could pick this one, all right, because I've said my velocity is 13 meters per second and it's not changing, which means I don't accelerate. But we could also use the general equation up here. Right? X final equals the initial position plus the initial velocity times time plus a half a times t squared, a being the acceleration, t being the time squared. All right. So let's plug that in. So x final is going to equal x initial, right, 0, plus the initial velocity times time. Well, our initial velocity and our final velocity are really the same thing. They're 13 meters per second times time, and in this case is 20 seconds, plus a half at squared. Well, and I'm going to put that down here. Well, a is 0, so it really doesn't matter what t is. All right, so this whole part of it cancels out. Okay, so what do we get? We get x final, as final position of our person, is going to be 13 times 20, which, if we do the math in our head there, turns out to be 260 meter mark. Okay, if I want to know the displacement, okay, the displacement d is equal to x final minus x initial. X final is 260 meters. Oops, I keep forgetting that 6. 260 meters minus 0 meters equals 260 meters. And that's how far the person would have traveled. And you know, we can use these equations, and they're fairly simple. But what's more interesting is if we have some problems where we have a bicyclist that may start at velocity of 0, bicyclist accelerates for a certain amount of time, and we'd like to know, say, how far that person would have gone in a particular amount of time. So let's do that. Let's scroll down here a little bit, and I'm going to recopy our equations from up at the top, and those equations are, let's see if I can do this here. All right, so magically I've recopied those equations from the top down to the bottom here. And what we want to do is we'd like to try a couple of problems using our new equations. So let's say that we have a bicyclist and the person is stopped. Okay, so our initial velocity, VI, sometimes also called V0 for V naught. So VI and V0 are sometimes interchanged. So VI or V0 is equal to 0 meters per second. Okay, and so our person takes off and accelerates at 3 meters per second squared. So the person is undergoing acceleration, and they do this for a time of 12 seconds. And we would like to know at the end of this 12-second period just how fast our person is going. Okay, so what is it we're looking for? Well, we're looking for the final velocity of our person. So if we glance over to the left-hand side of the screen, which equation will give us the final velocity? Well, the top one won't. The second one certainly will. It has v final in it. Okay, the third one will not. This gives us x final, and the fourth one has v final in it. Okay. But it also is assuming that we know the displacement that our object or bicycle traveled, and we don't have that initial information over here. Okay. However, we do have time, so we got that one. We have acceleration, and we have initial velocity. So we can get v final using the second equation. And that's one of the key things in solving these problems, is identifying the information that you've got and what it is you're looking for. All right? Then you can go over to the left-hand side or your equation toolbox and pick out the right equation. These equations are your tools. All right? It's like building a house. You've got screwdrivers and saws and hammers and all kinds of different things. Well, if I need to hammer a nail into a piece of wood, I'm not going to use a screwdriver. Right? So you've got to pick out the right tool. And in this case, we need to pick out the right equation. One of the other tools that I use is I like to keep my data organized. In physics problems, it's incredibly important to organize your data and keep a good accounting of it. I create tables. I'm big on creating tables and keeping my data in tables, and that way things don't get lost. We're not all real organized people. Some of us are more organized than others. Some of us struggle with organization. If you use a table like the one over on the right-hand side, it makes it that much easier. So what I'm going to do is I'm going to populate my table. Our initial velocity is 0, so VI in the x direction. And notice I've got subscripts over here. It's not just VI, right, initial velocity, but it's the initial velocity in the x direction. That's what my subscripts are for. They label what my data is. Okay. Let's see. So that I've got my acceleration, and that's 3 meters per second squared. Right. I'm not putting the units in right now because I'm afraid I'm going to run out of room a little bit here. Actually, I should have these on the other side. Let me do that. There we go. Let's put these over here where they belong. So 0, and maybe I do have room, meters per second, and 3 meters per second squared. What else do I have? I have a time of 12 seconds. Okay, and that's all the information I've got. What I'm looking for is V final in the x direction. I can use the second equation. So V final in the x direction is going to equal V initial in the x direction, which is going to be 0 meters per second, plus a times t. Well, it's going to be the acceleration in the x direction, so 3 meters per second squared, times the time, 12 seconds. All right, and that's it. All right, so we do the math here. 3 times 12 is 36. This seconds cancels out with the squared term there, and we're left with 36 meters per second, which would be our final velocity. Okay. Now let's say after that 12 seconds, we know we're going 36 meters per second. How about if I wanted to know just how far I traveled during that 12-second period? Well, how far is x, or its displacement? The equation that I might be interested in would probably be the third one down. All right? I want to know my final position if I know my initial position. So I'd like to know just how far we go in that 12 seconds. So let's use that equation. X final equals x initial plus V0t plus a half at squared. Now, one of the beautiful things about doing these kinematics problems is we can decide where our starting point is. Unless the problem itself tells us where the problem is, we can decide where it is. And you know, to make life easy, if I have a coordinate system here, and this is x and this is y, if I want to make my life easy, I'm always going to pick my beginning point to be 0. Right? If I pick my beginning point to be 0, that means x0 equals 0, and it makes my equations a little bit easier. All right? So I will always do that unless it specifies that I'm starting at some position like 5 or -5 or 10 or whatever the case might be. Okay, so moving right along here. Let's see, so we want to know now what our final position is and then what our displacement is. So we're going to use x final equals x initial plus V0t plus a half a t squared, and we're going to get our position from that. Right? So x final is going to equal x initial, which is 0, plus vi times t. Well, our initial velocity is 0, so 0 times t, plus 1/2 times a, our acceleration, which is 3 meters per second squared, times t squared, which is going to be 12 seconds squared. We just almost ran out of space there. Now, what I should have done also is added these variables up into my my table up here. All right, but I'm looking for xx, and actually I've got everything else. Okay, so I can just plug them in without having to do any additional work. So 12 times 12 is 144. All right, times 3. Let's do the math here. When we plug these into our calculator, what we should come out as 216 meters is our x final position. Now, since I chose x initial to be 0, all right, my displacement is going to be x final minus x initial, which is going to be 216 meters. All right. This is why I generally always pick x initial to be 0, which means that when I get my x final position, that's the same as my displacement. Okay. You do have to be careful because it won't always be the case. All right. So let's scroll on down. Let's try a few other problems here. Notice that in these tables that I've got over here, I've got two different kinds of tables if you look very carefully. One is for x data, right? It's x sub x, a sub x, vi sub x, v final sub x, and t. And then I've got x sub y down in this table here, x sub y, a sub y, vi sub y, vf sub y, and t. Notice that there is no subscript for t. T is the one variable, time is the one variable that does not matter whether it's going in the x direction or the y direction. We'll use that much, much more when we do kinematics in 2 dimensions. But time has no dimension, either x or y. All right, speaking of the y direction, let's try doing a problem in the y direction. Let's say that you, whoops, are on top of a cliff here. A funny cliff. All right, there's you. And you have a rock. And let's say that our cliff is 10 meters in height. Okay? And like I said, now this is where it gets really important to choose your coordinate system. Okay? I'm going to choose my coordinate system. My 0 point on my coordinate, whoop, I shouldn't have drew that poorly. That's, I'm going to redraw those. My coordinate system is where we're going to drop my rock from. Okay, so my rock is going to be at my 0, 0, and my, it's going to be 10 meters in height from the point where I drop the rock to the ground. Okay, so I need to specify that a little more carefully. All right, so this is going to be my 0, 0 point. So my x position, right, initial, is going to be at 0, and I'm going to call that x initial in the y direction. All right, let me make that a little bit better here. X initial in the y direction will be 0. Okay. X final in the y direction will be what? Well, if this is 0, this point right here, right, and I'm going to be dropping this rock down to this position here, I'm going to be going in the negative x direction. I'm sorry, the negative y direction. And so my final position, my x final in the y direction, all right, and x is really, x doesn't mean it's in the x direction. X is my position variable, okay? So my position variable, x, the final position in the y direction, is going to be at the negative 10 meter mark because I'm starting up here, right, at 0, 0. All right, that's at the y equals 0 position. So if I'm traveling down, all right, then my final position must be negative. All right, and so it's negative 10. All right, acceleration. Okay, we haven't really talked about acceleration, but the acceleration for anything that is thrown up in the air or dropped is always going to be the acceleration due to gravity. The acceleration due to gravity is always going to be 9.8 meters per second squared as long as we're at the surface of the Earth. And most of the problems that we do are going to be at the surface of the Earth. If we were up at the top of a very, very, very high mountain, instead of negative 9.8 meters per second squared, it would be negative 9.7 meters per second squared. Now, excuse me, why is the acceleration negative? Well, which way does the acceleration cause something to move? It causes something to move in the negative y direction. And so it's critical that we get the signs of these things right. Okay? So not only is our displacement in the negative direction, but our acceleration is also in the negative direction. Okay? My initial velocity in the y direction, right? I'm holding a rock and I'm just going to let it go. At the instant that I let it go, the velocity of the rock or whatever object I'm holding is going to be 0. So anytime I simply drop something, I don't throw it, but I just drop it, my initial velocity in the y direction will always be 0. Okay? My final velocity is something in the y direction, is something I'd like to figure out right now. Okay? Now, what equation should I use? Well, we have x in the y direction. We have the initial value of x. I should add a row here, and I should have x initial in the y direction. This should be x final in the y direction. Okay, x initial in the y direction is 0. Okay, x final in the y direction is going to be negative 10 meters. Acceleration in the y direction is going to be negative 9.8 meters per second squared. Vi in the y direction is 0. V final in the y direction, well, this is what we want to find, okay? And the time in the y direction we do not know, okay? So we're going to need to scroll up here a little bit, and I'm going to recopy these equations back down in a second here. So I've recopied the equations over on the right-hand side over here, and what we need to do now is we need to look at the information that we have and pick out the right equation. Well, we're looking to find out our final velocity. So this is one equation I might be interested in. All right? Final velocity is equal to initial velocity. Well, I know what that is. It's 0 plus a times t. Well, I know what the acceleration is. It's negative 9.8 meters per second squared. But I don't know the time. So that's a problem. I've got one equation, I've got two unknowns. So that's not going to help me that much. Okay? But I have another equation down here. It says v final squared equals v initial squared plus 2 times a times the change in my displacement. Well, do I know the change in displacement? Yeah. Do I know the acceleration? Yeah. Do I know the initial velocity? Yeah. So I know all those things. So I can use that final equation there and plug these in and find out what my final velocity is. So let's do that. So Vf in the y direction is going to be v initial in the y direction. Well, v initial is 0, so it's going to be 0 squared plus 2 times a. Well, a is negative 9.8 meters per second squared times the displacement, x final minus x initial. Well, x final is negative 10 meters minus 0 meters, because that's x initial. All right, so what do we got? I should have a squared term over here. Apologize for that. So negative 10 minus 0 is negative 10. Negative 10 times negative 9.8 is 98. 98 times 2 is 196. So v final in the y direction squared is equal to 196 meters squared per second squared. Okay? If I now take the square root of both sides, I get v final in the y direction to be 14 meters per second. Okay? So all I really did was collected my information over here, right? Picked out the right equation based on the information that I had, and then plugged in the numbers. Now, we could also find out how long the object was in the air for. So let's plug this 14 meters per second in over here, and let's see if we can find an equation that would get us the time. Well, let's see. We have a couple of equations here. We have this one here. We could get time using that one, but it's got a squared term up there, and that's kind of ugly. We also have this equation here, v final equals v initial plus at. All right, that one might be a little more palatable to use. So let's see if we can use that one. So, but we have to be very careful with the signs here. Okay, so v final. Now, I should point this out ahead of time. Okay, v final that we came up with turned out to be 14 meters per second squared. What was the direction of the velocity. Was it not down? It was, right? And so one of the things, one of the downside of using this equation down here is that because the terms are squared, we lose the sign of the velocity vector. And so you've got to inspect the problem and see just what the direction of that velocity should be, and make sure that you add in the sign when all's said and done, all right? Because our velocity in this case is negative, okay? So that's the one caveat to using that equation right there, all right? So V final equals V final equals V initial plus AT. Well, V final is negative 14 meters per second equals V initial, which is 0, plus AT. Well, A is negative 9.8 meters per second squared times T. So if we divide each side by negative 9.8 meters per second squared, we get negative 14 meters per second divided by negative 9.8 meters per second squared is equal to the time that the rock was in the air, and it turns out to be about 1.428 seconds that the rock was in the air. Okay, so this is how we use the kinematics equations. All right, what's important? What's important is picking out all the data, using a table similar to the one I've used on the right-hand side. In the future problems, what I am going to do is I am going to add another row down here, so I not only have x in the x direction, but I have x in the x direction initial and final, okay, so that we can use these equations. All right, so I hope that helps. If you need to see more problems solved, I'm going to be doing quite a few of them. I'm going to be adding them to the YouTube channel, so watch those and hopefully those will help. Thanks and have a great day.